This is the function set for chapter 3. I've talked to you about part 1 already, the fruitful functions, the ones with return values. That's the part that unit tested. But now let's skip to the second part and talk about that. So scroll down past the monstrous number, which perhaps you've written the code that reproduced that. It's called tetration. Actually, the code as I ask you to write it, uh, it of necessity executes so incredibly slowly that it would not be able to ever produce that number. I produced it in another way. Sort of a joke, actually. But anyway, so here we are, part 2, the fruitless functions. This is where you draw, okay? As for how I'll actually grade them, the way that I'll grade them is this, is I will actually call the functions. You'll write a number of functions, the ones described. I will call them, and then it will draw to the screen, and then I'll just watch them, okay? And if they're visually sufficiently similar to what they're supposed to be, you'll get full credit. But if they're like really off in some way, then you won't. I mean, there's, for instance, like a grid of squares. Does it have to look exactly like that? No. Does it have to be like visually identifiable as a grid of squares? Well, yes, of course. So long as it is, you'll get full credit. Before we actually launch into this, the technical details of this, let me make sure you understand why this is in an iteration chapter. Okay, so the basic idea behind iteration is like you've got this chunk of code that executes multiple times, right? You go through it once, you go through it the second time, the third time, and so on. Now, perhaps something modifies, changes each time you go through it, but it's still the same block of code. Okay, what we had was, a value of a variable would change, but still the same code would execute again. Here, well, it might be the value of a variable that changes, but really what is visually obvious about what changes is position, okay? Like, look at the top row of squares. I mean, you draw a square, you move over, you draw it again. You move over, you draw it again. You move over, you draw it again. The again part is the iteration, okay? The variation is that you've moved over. But that screams iteration, okay, in computer science. When you see something like this, and it's repetition, it's something done multiple times, that's iteration. But notice this as well, and we talked about this last time, it's actually iterated iteration, okay? Like one iteration would produce a row of squares, but then you've got multiple rows of squares to produce, right? So the iteration that produces the row of squares is itself iterated. That's iteration inside of iteration. And actually, the real way this will be modeled as iteration inside of iteration inside of iteration, because one square itself is really iteration. Why? Draw side, turn, draw side, turn, draw side, turn, draw side. So it's that process repeated, that is draw side and turn. So one square is iteration. A row of squares is iterated iteration. A grid of squares is iteration that is iterated, that is iterated, okay? It goes 3 levels deep. And what's so wonderful about this, and I ripped this idea, this is very commonly done when you introduce Python, is you draw. But the reason I do it here is because it's like sort of the natural visual representation of just what iteration is. So that's why we do it here. Oh, and you've got some others as well to do. And I provided pictures for you. I want you to draw a spiral. And then here's something that I call the Liam square, because it was, Liam just began to play around last year just to draw this or that, and said, hey, look at this. And I said, hey, that's cool. I'll make everybody do that. So you get to do a Liam square. And they're all iterations. Do you see the iteration in the Liam square? Of course you do, right? It's a line, and then a line, and then a line, and a line. There's variation, of course, but it's the same basic process with variation. All right, so go back up to the top to the instructions. There is a tool that you will use, okay? The tool is called Euclid. I created this tool. Well, actually, I just basically relabeled some other tools that are out there and simplified them a bit. But this particular set of tools called Euclid is my creation. So if you were to click on that, as I just did, you would be taken to another page of my website, which is the official documentation for Euclid. I'll talk about some of this for sure, but I will not talk about all of it. So a number of capabilities of Euclid that we don't really need at this moment in time, well, they're described here. So if you wanted to go and read about them, that's fine. And also everything that I will talk about today is described here. So you might want to hop over to the official documentation if you're confused about something and read, or talk to me, of course. So go back to the instructions. Okay, so you're back here, right? I have begun the second part of the project for you. So you see the second link. It says, I've begun a project at REPL for you. This one, click that. You will not see a screen that looks like this because I am the owner of this project and you are not. What you will need to do is this. You will need to go and hit the fork button at the top right. You see the fork button? Fork. This project is now, it has been now copied and it resides in your list of REPLs. And this is what you'll continue to work on. This is what you'll fill in for part 2 of the project. And I will go through this in some detail with you. But if you were to scroll down for a little bit, once you hit line number 46, these are the function skeletons that you will have to fill in. You'll have to write a square function, a row of squares function, a grid of squares function, and so on. Okay. All right. Let's talk about what's here, because I do want you to have some idea of what all this is. So first of all, look on the left-hand side, okay, in the file structure. There are 3 files that I should discuss. The first is just simply main.py. That's what is open right now. When you open up a project, you always automatically go to main.py. If you had not yet realized this, what happens when you hit the run button is it executes the Python code that resides inside of main.py. That's just what the run button does, always, okay? Now, there could be other files there other than main.py that contain Python code, and in this case there are, but they will not automatically execute. Okay, what automatically executes is main.py when you hit the run button. Now, I have created 2 other files here, one colors.py, the other euclid.py, that are Python code. And I'll talk about how those get executed in just a moment. But I wanted to look for a moment at the contents of these. First of all, at colors.py. All right, so Euclid is a tool to draw. It would be nice to be able to draw it with various colors on various backgrounds. Draw with pins that are differently colored, or draw on backgrounds that are differently colored. Here are convenient color names for you, and I did not create these. These are standard, and they're used not only in Python, but in many other languages as well. I first came across them when I played around with HTML a little bit, and then got bored and quit. But I thought it was cool that these had names. Okay, so there apparently is Alice Blue. That consists, notice this, okay, that is a variable assignment statement, right? On the left-hand side is the variable name, Alice Blue, capitalized, because we'll never change the value. Capitalization means that it's a constant, it will never change. But apparently that variable, Alice Blue, designates 3 numbers, the triple, and they are 240, 248, and 255. I thought I would explain a little bit about what those are. Well, this is the RGB color model that you've just run up against. Do you know what the R, and the G, and the B stand for? Red, green, and blue. That's exactly right. Now, how do we produce color? We mix degrees, intensities of red, and green, and blue. So that 240 is an intensity of 240 of red. An intensity 248 is an intensity 248 of green, and the 255 designates the blue. Okay. Now, as for the possible values you could have for any of those 3 numbers, they all lie in the range 0 to 255 inclusive. Okay, so 0 is the least intensity of any of the colors, and 255 is the greatest intensity. So how many total values is it then for each of the 3 shades, red, green, and blue? How many reds are there? 250. It goes from 0 to 255. 6, because we started 0, because in computer science we started 0. We just do. We always do. Okay? So there are 256 possible shades of red, possible shades of green, and possible shades of blue. And it's actually quite curious then to look and see how many total possible colors we have in this model. Python is a wonderful calculator, so let us make it calculate. So 256 to the 3rd power is, excuse me, this is the console inside of Pygame, which doesn't work sometimes as expected. So go over to shell. Are you in shell? You click shell, click shell. Now type Python. Now we're in the Python console. And now we can cube 256, which is a little under 17 million. So in the RGB model, where we have values of 0 to 255 for each break complete, we can produce a little bit under 17 million colors, which is quite incredible. And here are some of them. Okay, here are some of them. Could you make others on your own? Absolutely, if you want to. You can just like choose three numbers randomly between 0 and 255. It produces a color. It's up to you ultimately, but these are convenient. It's cool to have them. Okay, so those are the colors. Now, euclid.py, this is a tool that I built a couple of years ago, and I built it on the back of a module called Pygame. Okay, Pygame, as the name suggests, is a module that allows you to write games in Python. It's a relatively quick way to draw graphics to the screen, though ultimately Python will never be as fast as a language like C, for instance, but it does work. What I did was I simply gathered up certain capabilities of Pygame that I thought would be useful to us as we began to draw, and I just made them easier to use. That's what this is. So if you want to poke through the code, you can absolutely poke through the code. It's not done yet. If you were to go down for a while, you would find certain functions that had not yet been written. There we go. Pass. So some are not complete, but it will do everything that we want it to do. Don't change this, okay? If you were to go in to change this file, probably you would break it. That means that you'd have to go back to my project and fork it again. All right, so let's go to main.py. This is where you will write your code, okay? Lots of comments to try to explain what happens here. And let me talk through it. And go yourself and read through all the comments at some point. Okay, so first line of code that executes, line number 3. Import Euclid. What does that do? Well, euclid.py is a file that contains Python code. Import Euclid executes that code, which will then mean that main.py will know all the definitions in Euclid, okay? And Euclid ultimately consists of just a set of functions organized in a particular way. It's a class, but ultimately it's just a set of functions. And after I import Euclid, that means that all the functions that are defined in Euclid are now known inside of main.py. Now, there will be a certain kind of syntax that we will use to access them, but that's what the import Euclid does. So I said before that the euclid.py file doesn't automatically execute. We can make it execute, and that's what line number 3 does. Now, line number 4, from colors import star. Well, let's try to make sense of why this is different than line number 3. They're both import commands. So line number 4 will execute the colors.py file, but the difference between them is this. Look down at line number 11, okay? And I'll talk more about this in just a moment, but I want you to look at the first part of it where it goes euclid.create page, okay? Here's what this means to Python. It means you imported a module. That's what they're called. When you import it, it's called a module. You imported a module called Euclid. Okay, there it is on line number 3. Import Euclid. And in that module is a function called create page. I wish you to call that function. And this is just the standard syntax for this. And it's not just Python. Other languages do this as well. For instance, Java does it like this. That's the dot notation. So it's euclid.create page. So that means go into the Euclid module. There exists in that module a function called create page. Call that function, okay? And we'll talk about the parameters on that function, the arguments in just a moment. But line number 3, okay, since it takes that form, since it says just import Euclid, the way that we get to the functions in the Euclid module is euclid.create, like line number 11, euclid.create page. We have to use the module name. Line number 4, on the other hand, okay, from colors import star. The star means that we will import every definition, and since it is this from colors import construction, that means that to get at those color names, we don't have to go colors dot and then the name of the color. We can just use the name of the color. We don't have to precede it with the colors dot. That's why it's done that, okay? But the upshot ultimately is this, is that lines 3 and 4 have to be there, okay? And don't change them, All right, so now let's talk about what Euclid does and how it does it. I intend this to be commonsensical. And this is part of a way to write code. We'll talk more about this later on. It's called the object-oriented paradigm. If you program much in Java, you've heard that without a doubt. But it's ultimately intended to be very commonsensical. It's an attempt to recreate sort of certain aspects of our world in code. In particular, our sort of common sense attitude towards the objects that are in the world around us, right? Like I'm an object, you're an object, the desk is an object, right? What makes the object that it is? Well, it has certain like properties, right? It's like, look, certain height, certain color, and so on. And it also has certain ways that it behaves. That's what the object-oriented paradigm does, and you're about to begin to see that, okay? So the first thing that I need to do is I need to create an object of a particular sort that is called a page, okay? That will behave very much in the same sort of commonsensical way that a piece of paper will behave. We will draw on it in particular, okay? And its only property or attribute is usually the word that's used here. Really, its only attribute, or only two attributes that are of real significance to us, are its size and its color, okay? That's what defines it. So you can see on line number 11, I call a function called createPage in the Euclid module. I give it an initial size of 400, 400, which could be changed, but you probably will not. And we give it a color of azure. And if you were to go back to the colors file, you can see what azure is. Is azure there? Yep, there it is. 240, 255, 255. That's a lot. Okay, so that creates the page. And we'll draw on the page in just a moment. That line of code needs to be left there. But you can alter it. You can change the size of the page. You can change the 400, 400, and you can change its initial color if you want. You can also specify its initial color, if you like, by a triple of three numbers between 0 and 255, because that's ultimately what a color is, okay? The colors.py file is just like shorthand for triples of numbers. If you would like to provide your own triple of numbers, you should do that. One other aspect of this that I need to talk about, okay? This was a function call, okay? Be clear about that. Okay, it's a function called createPage that lives inside of the Euclid module, but it is a function call because it's named followed by open parentheses, createPage, open parentheses, function call. But the way that I have sent values is different, okay? Notice that I wrote size equals 400, 400. I wrote color equals azure. We haven't seen that in function calls before. In function calls before, you would have had just something like the 400, 400. That is the value that gets set. And then what is the size? And what is the color? Those are the parameters, okay? If you were to actually look at the function definition inside of Euclid, you would see that its parameters are size and color and tracer. And the reason, well, first of all, Python allows you to include the parameter name if you like when you call the function. So you can go parameter name equals value, the argument that will be sent to it. You may do that if you like. And there are various reasons to do it. The reason that I do it here is clarity, so that you will understand what these numbers represent. That the 400, 400 represents the size of the page. The azure represents the color. Okay, and tracer, we won't worry about that right now. That's a way to speed up animations. Sometimes if animations get really complex, they can really bog down, really slow down. Tracer is a way to get past that, so we don't worry about that now. But yeah, so you'll need line number 11. You've got to have the page. You cannot draw if you do not have the page. But you can change the values of the attributes, size, and color if you like. You can play around. All right. So we've got a piece of paper now. We also need something with which to draw. And I call that simply a pen. Okay. So the Euclid.pen construction on line number 17 creates a pen. And then, because I wanted the possibility that we would have more than one pen, I set it up in such a way that the pen, once created, could be assigned to a variable. Okay, so logos assignment token, that's a variable assignment statement. Okay, so the pen that we're about to create here on line number 17 is called logos. Call it whatever you want. It makes absolutely no difference at all. Okay, it's just a typical variable. Okay, so what happens on the right-hand side of the assignment token? I create an object of the pen type. What defines a pen? Well, seems obvious enough. The color with which it will draw. I chose its color to be blue-violet. I also chose its initial position as 0, comma 0, and I chose its direction as also 0. And we have to talk about what that means, okay? Because what it means is perhaps a little unexpected. What it means is likely different than what you've done in an algebra class. Position 0, comma 0. Okay, so we've got this page, right, on which we will draw. 0, comma 0 is the top left, all right? It's not the center. It's not like the origin, like when you're in your algebra class. It is the top left. Why is it like that? Because that's how digital images are always handled, okay? In any kind of a digital image, 0, 0 is top left of that image, okay? And what does direction 0 mean? Direction 0 means that you point directly right, okay? That you point directly right. And what you must also understand is this, is that as you rotate counterclockwise, that is an increase of angle measure. Okay, so 0 points directly to the left. So how do you think 90 degrees points? Counterclockwise is increase. Straight up, right? So 0 degrees. Okay, so I've got this image, right? 0, 0. 0, 0 is top left. 0 degrees points to the right. Counterclockwise is increase of degree measure. So that is what? Directly up is 90 degrees. What's directly left? 180 degrees. What's directly down? 270 degrees. And yes, you can continue all the way up to 360, but that's equivalent to 0. Would you like to guess what my code does to determine that 360 is equivalent to 0?
360 divided by 0.
Remainder. I just always do the remainder operation, and what's left is the degree measure. Okay, so counterclockwise is increase in angle measure. Clockwise then would be what? Decrease. So if I use negative angle measure, what is directly down? Negative 90. And the negative 180 will be directly left, which is equivalent to positive 180. Any two degree measures that are separated exactly by 360 are equivalent to one another, because 360 is one complete turn, same direction as you had before. And if you use negative 270 points directly up. Euclid doesn't care. Use positive, use negative, write code in such a way that it gets very negative. Euclid doesn't care. It will convert it into what it's equivalent to. Okay. So that's how position works. That's how direction works. A very good question at this point is like, why make direction work like that? Why have 0 degrees point to the right, and why have increase correspond to counterclockwise rotation? The answer is that that's the way that it's done in mathematics. Okay. And moreover, I don't think it'll happen in this chapter, but it'll happen in later chapters, like the project we do at the end of the semester, that there will be certain mathematical functions that I will introduce to you, trigonometry, that you will want to use. They're immensely useful to calculate positions in any kind of a coordinate system. And ultimately, a digital image, a collection of pixels, is a coordinate system. Okay? If you ever wondered in an Algebra 1 class, it's like, why the hell does this make any difference? Why do I have to learn about coordinate systems? You look at a coordinate system probably on the neighborhood of 4 to 6 hours a day. It's your phone. That's what that is. It consists of pixels. And they have position, and they have X and Y coordinates, literally. That's how that works, okay? So as for why it is that direction 0 is left and counterclockwise is positive, that's the way you do it in math. So if you wish to be able to use mathematical tools to like calculate positions, and you do, you have to do it the way the mathematicians do it. So of course, it's done in computer science the way that it's done in mathematics. Okay? All right, so that's a bit of the story about position. And there's another part about the story position that I have to say. Okay, so 0, 0 is where? Top left, right? As I go right, X increases. X is the first coordinate. That's just like algebra. However, there's a difference. As I go down, Y increases. Okay? As I go down, Y increases. It's like flipped from mathematics. It's the way that it is. And what that means is this, is that you never have negative values for the coordinates of a pixel in a digital image. 0, 0 is as small as it gets. Okay? Well, here's a question for you. Okay, so the 400 by 400, which was the page size, that's the number of pixels. Okay, so it's 400 pixels long by 400 pixels high. But that initial pixel is at 0, comma 0, top left. So what are the coordinates of the pixel at the bottom right? There are 400 total pixels, but we start at 0. So it has to be what? It has to be 399. Okay, so the coordinates of the pixel in the bottom right-hand corner for this page that's 400 by 400 is 399 by 399. And do you need to know that? Potentially, yeah. Okay, because very often you will use the x and y coordinates of pixels when you draw. Okay, so we've got the page, we've got the pen, which is called logos. And then let me show you how you would use this to actually draw. So here's a very simple function. It's called draw triangle. And we're about to iterate because triangles very naturally involve iteration, right? Draw side, turn, draw side, turn, draw side, turn. Okay. Well, here it is. Depth draw triangle with 3 parameters, s and x and y, which should make sense. You need a side length, and then you need the coordinates of some point on the triangle, which for us will be the lower left-hand corner. So what this function will really do is draw a triangle, a side length s, whose lower left-hand corner lies at the coordinates x, comma, y. Now, line number 23. We have to give orders to logos, okay? And there is a standard syntax to do that. It's logos dot, and then the name here is called a method, okay? It's ways that our pen can behave. Okay, so what we tell logos to do is literally lift up off the page. And the reason we do that is because we wish to move logos and not have it leave a trail, not have it mark as it does that. Okay, so logos dot up. That means pick logos up off the page. Notice the parentheses after up. That's a function call. Okay, that's a function call. If you were to leave the parentheses off, the code would not crash. It instead would just be the name of the function, and you would not have called it, and the code will not behave in the way that you expect. Okay. So what we do is we pick logos up, and then we tell logos to go to the position x, comma, y. That's where the triangle will begin, and then we put logos down. Okay, so logos step down. So logos get up, logos go to x, comma, y, logos get down. It's a very sort of commonsensical, natural idea. Once you get used to the syntax, okay, the order, that is what it is that you tell logos to do, comes after the dot, okay? That's the method name. All right, and then line number 26, we begin the iteration for underscore, that's true, for underscore in range 3. Well, the range 3 is no surprise. I want to draw a triangle, so I need to do something 3 times, right? Draw a side 3 times. So the range 3 is perfectly expected. Now, what's up with the underscore? That's the loop variable. A for loop always has to have one of those. But in this case, we will never use it. Okay? Look at lines 27 and 28, the body of this loop. We do not use the loop variable. We do not use the underscore. It doesn't make any difference what it is. But it has to exist because that's how Python constructs iteration. And typically what Python programmers will do when they wish to set up a loop, but the loop variable will never be used, and it doesn't matter how you spell it, they'll just use the underscore, okay, which is a perfectly valid variable name. Remember the rules of variable formation. You can use letters, you can use numbers, you can use the underscore. You can't start with a number. That means the underscore by itself is a perfectly valid variable name, and it just communicates to programmers. It's like, hey, I'm never going to use that. Okay, so lines 27 and 28, that's the body of the loop. Those will execute 3 times. So I tell logos to go forward by the length s, okay? And that s will then be in parentheses to tell logos how far forward to go. So logos will go directly to the right because logos' direction, as we talked about a moment ago, its default direction, its initial direction, is 0 degrees, which points directly right. So logos will go to the right a length of s, and then logos will turn 120 degrees, and then logos will do it again. Now here's something that you will wonder about. You will wonder why that's 120 instead of 60. Because after all, what are the angle measures of an equilateral triangle? They're 60, right? So you might wonder, well, why isn't it 60 here? Okay. Well, the thing is this. Okay. I'll draw it up on the board. Okay, so we're like going directly to the right, right? So we've got to link the base, the direction 0 degrees. And then we wish to produce our next side, right? Our second side of the triangle. Well, yeah, the angle of the triangle, the internal angle of the triangle will be 60 degrees, but that's not the angle we want. We want the angle from our original direction, which I continued out, to the new direction. That's the angle outside of the triangle, not the angle inside of the triangle. And if the angle inside is 60, what is the angle outside? Because what do those two angles together have to measure? 180, right? So that has to be 120 degrees. This will matter, okay? This will matter because one of the functions that you have to write is a function that will draw a regular polygon. So you've got to be able to figure out for a given number of sides in a regular polygon how much you should turn. And if you think it's the internal angle, you will not get it right. It's the external one, okay? It's the external one. All right, so there it is. There's the iteration for underscore in range 3, forward, and then turn, forward, turn, forward, turn. And then it should draw a triangle. So scroll down a little bit. There are function calls near the bottom of the code. I will comment out line number 77 because I don't actually wish to execute that one. The one that I wish to execute is the one on line number 73, which draws a triangle. Ooh, and I use named arguments in this case. So side length 150, x coordinate 100, y coordinate 100, and then we can run this. And we might have to wait a little bit. This is slower than it used to be. Yeah, please.
The code I got online only goes to 124.
Yeah, I think you clicked on something that was on the Euclid page. Go back to the functions page for chapter 3. I'll hop over there real quick. I had some other people do this too. So, okay, so make sure you've got this page up. You got this page up. And then there's a link that says this one. I'll make it big. So that one right there. This one. That'll be the long one. Okay. That'll be the long one. And that'll be the one that all you'll have to do is continue on. Right into it. All right, so I don't know why it takes so long. It didn't used to take so long. Sometimes it will decide that it has to update Pygame. So we'll give it just a second here. A heads up about another tool that you could use. It's called Python's Turtle module. It's been around for a long time, and it's powerful and very commonly used. I didn't want to use it because of certain of its features. I wanted my alternative tool. However, and every year I have students who are familiar with the Turtle module. If you'd like to use the Turtle module to draw, ultimately, I don't care. What I do care about is that your visual output looks right-ish. Okay, so my triangle is so big it's off the screen. I tell you what, I'll move it down a little bit. Bound would mean that I have to increase the y value. So let me hit stop and then run again. Yeah, there we go. So I drew a triangle. And I want to show you one other bit of code just to drive home the point that the whole point of this, how do you draw? Why I have you do that is to get you familiar with iteration, to get you comfortable with it. So I'll call a second function that's called try-line that will produce a line of triangles. That begins back up on line number 34. So that's a function that takes 4 values. N is the number of triangles it will draw. S is the side length, at least the initial side length of the triangle. X and Y are the position of the first triangle that it will draw. Okay. So line number 35, we start iteration for underscore in range N. No surprise about that. We wish to draw N triangles. And then line number 36, we call the draw triangle function, which of course we could do. We defined it above, so we can call it. But notice that the draw triangle function itself iterates. That means that we really have iteration inside of iteration, which again is no surprise because we'll draw this line of triangles. And so that's iteration. It's multiple triangles, but each triangle itself involves iteration. And then I just played around a little bit. Like line number 37, S is S times 0.5. What happens to a quantity when you multiply it by 0.5? Smaller, right? Half as large as it was before. So I shrunk the side length because, why not? And then I also redefined the x and y values, so the new triangles, the new smaller triangles would be in different positions. Mostly I just sort of played around. This is an example. And then let me make sure. Yep, the triline function has been called, so I'll execute the code, and then, hey, look, it's a line of triangles. Okay. So what do you need to do? What you need to do is, well, of course, go and read the function descriptions back over at Think Functional, but then you'll need to write these functions that begin on line number 46, the square, row squares, and so on. Okay? That's what you have to do for part 2 of the project. All right. I know that I just dumped quite a bit on you. This is quite a bit of information. But I think it's important to tell the whole story more or less complete all in one go. I'll come back and review a little bit next time, but honestly, for the most part, I've had my say for this chapter. Most of the time that remains to you will be time that you will work. Okay? And there won't be many days this year where I will have to do something like what I just did. That is to talk for this long.